Today's last speaker is Krishnendu Sengupta from the Indian Association for the Cultivation of Science in Kolkata. He'll tell us about his work on transport in topological junctions.
Okay, I'd like to start by thanking the organizers for inviting me here. And so the topic of the talk today is transport in topological junctions. And this is a work that I did recently with my former postdoc, Devabrata Sinha, who is now in IOP Bhubaneswar as doing his second postdoc. So the outline of the talk is the following. So first I'm going to talk sort of give a basic introduction to this kind of transport calculations in topological materials, and as a case study talk about Dirac electrons in graphene. And after that I'm going to come to the main subject of the talk, which is transport in junctions between a Weyl and a multi-Weyl semi-metal. And we are going to show that the normal metal barrier, normal metal, and N-B-S, that is normal metal barrier superconductor, junctions of this kind of materials essentially shows a completely qualitatively different property, which is not seen in the other junctions which was studied before. And this will be followed by conclusion. So let's start from real basic thing. And this is a quantum mechanics problem that we all solve in our second year of PhD maybe. So you put a barrier and you study transmission through that barrier, and what you know is that as you increase the strength of the barrier potential, your transmission is a monotonically decreasing function of the barrier strength. Now this simple fact essentially gets into tunneling conductance calculation of almost any material. One of them is this normal metal barrier and normal metal interface, where if you increase the barrier strength, your transmission and hence the conduction decreases. This also shows up in N-I-S interface, that is normal metal insulating and superconductor interfaces, where if you calculate the transmission, there is a contribution from Andreev reflection, which is a new phenomenon that comes up whenever superconductivity is involved. That is, if an electron approaches the barrier, a hole can come out, and there is a charge transfer, YZ charge transfer. But as the barrier strength increases, in this kind of materials where the quasi-particles obey Schrodinger equation, the Andreev tunneling process is exponentially suppressed, and therefore the tunneling conductance within the gap decays with the barrier strength. So you can see that it goes, so this Z is the effective barrier strength, and as I increase Z from 0 to some large value, the tunneling conductance just goes down. Okay. So in most of the cases, whenever there is Schrodinger electrons involved, the bottom line is that if you increase the barrier strength, tunneling conductance, and hence flow of current is going to decrease, and this comes the standard tenets of quantum mechanics. And just as a maybe I'll just keep let me just tell you that the calculation that one does in this kind of systems is done using a formulation that Blondert, Tinkham, and Klapsik pointed out a long time back. And the idea is that you let an electron or electron-like quasi-particle incident on the barrier from the normal side, and then allow for both a reflection and an Andreev reflection, and then match wave functions and its derivatives at the barrier, and obtain R and RA, and then calculate tunneling conductance by this so-called BTK formula. Okay, so that's the standard thing. That's what we do normally. Now, when it comes to Dirac electrons, so for example, for graphene, what happens is that these electrons have a linear dispersion, and there are various properties. The one thing is that they have helicity property. So, for example, for graphene, the pseudo spin along the K point that moves around the K point that moves along the direction of its motion. Whereas for K prime point, it moves opposite to its direction of motion. And the other thing is that the density of state varies linearly with E, that is the energy, which is different from standard materials where it's a constant. So what happens if we take this potential barriers problem and solve it for a standard Dirac electron incidenting on the barrier? And now, when one does this, one immediately sees that the answer is very different. and without getting into the details of the calculation, one can, so just to note that if you're in the thin barrier limit, which means that your V0 is very large and D is rather small, so that the product V0 times D is a constant, and chi is the dimensionless barrier strength, which is that constant in units of H per VF, the transmission becomes an oscillatory function of the barrier strength. So there are two interesting points here. One of them is that if the particle incidents normally on the barrier, you see that the transmission is unity. That's known as the Klein paradox, and there are various ways of addressing that. But our main focus would be on, for any angle of incidence, transmission is 1 if this chi is an integer multiple of pi. Okay. So the transmission resonance, that's the transmission resonance condition for Dirac electrons. And the basic point is that the transmission, and hence any conductance that you calculate, would now be an oscillatory function of the dimensionless barrier strength. That's omnipresent in most of these topological materials. And if you look at a normal metal superconducting interface of graphene, it's a work that we did quite a long time back with Subhro, who is in the audience here. One sees that if you calculate the tunneling conductance of this junction, it gives you an oscillatory function of the barrier strength. Okay, so the tunneling conductance oscillates with the barrier strength rather than decaying exponentially. So these two properties are the two basic qualitative properties of tunneling conductance and of this kind of junctions. If the junction quasiparticles obey Schrodinger equation, then they are going to decay monotonically with the increasing barrier strength. And if they obey Dirac equation, they are going to sort of oscillate with the barrier strength. This is seen for almost any junctions that people study. And you see that this oscillation is not just a property of the thin barrier limit, but even if you make the barrier thick, these oscillations persist. It's just that their amplitude decreases and period widens with the barrier width. So these oscillations are robust. So, but in the kind of junctions that I'm going to talk about today, there is a third kind of property that shows up where the tunneling conductance becomes completely independent of the barrier strength in the thin barrier limit. So you change your barrier strength, nothing happens to your conductance. And so let me try to see how that comes up. To do that, let me just introduce briefly some properties of this Weyl and Multi-Weyl semimetals, which I'm going to use in the calculation. So Weyl Fermions are, their origin comes from high energy physics, where it was noted that in odd dimension for massless fermions, Dirac equation can be further simplified. And by appealing to the fact that there is a matrix gamma 5, essentially which commutes with all the products of gamma 0 and gamma I, and apparently using that you can express this massless Dirac fermions as in, massless Dirac fermions are also eigenstates of gamma 5, and therefore you can get this massless chiral fermions. So these are the Weyl fermions that show up. Okay. Now in condensed matter system, this kind of stuff appears by crossing of bands. So Weyl structure of effective 2x2 matrix Hamiltonian in terms of the sigma matrices essentially comes out of band touching. So conductance, if conduction and valence band touch at some point in the Brillouin zone, and if this touching is robust, which is protected by some kind of symmetry, then essentially you have this Weyl structure. And the crucial role in this is played by time reversal and inversion symmetry. And to understand that, let us just think of this in the following way, that typically bands in a material could be degenerate due to several symmetries. So you could have spin rotational symmetry, or time reversal, or inversion symmetry. And you need to break at least two of these so as to get non-degenerate bands, which may then cross at special points to give you this Weyl structure. Now, spin rotational symmetry is usually lifted by spin-orbit coupling, okay? And so, for example, let's take the case where we sort of break this time reversal symmetry. Then you see that these non-degenerate bands essentially can cross at time reversal invariant momentum points. And if you have a crossing at k0, there would be another crossing at minus k0, and so on. And so the point is that these crossings will always happen, but to have a Weyl structure, you need these crossings to occur at Fermi momenta. That's another constant, and that's why Weyl materials are not so omnipresent. There are only a few of them. And such crossings always occurs in pairs, and there should be at least 2 such crossings within the Brillouin zone. And that can be understood very easily in the following way. Just think that there is only one Weyl point inside the Brillouin zone, and then you draw a circle around your gamma point, a small one, and you sort of calculate the Berry curvature around that circle. Now, because you are not enclosing the Weyl point, which is, let's say, somewhat further away from the gamma point, you're going to get a 0. Now you extend this circle, at some point you're going to get 1 because you have now enclosing one Weyl point by increasing the radius of that circle. Then you keep doing it and you end up at the edge of the Brillouin zone. Okay. Now the question is, the edge of the Brillouin zone is exactly same as your gamma point, so you should get a 0, but this cannot change because you haven't done really anything substantial. So which means that as you go from the edge to the from the center to the edge of the Brillouin zone, you must enclose an even number of Weyl points to have consistency. Okay, so and that's why it should occur in pair, at least in lattice systems where there is a finite Brillouin zone. So if you look at the generic low energy dispersion of these Weyl nodes, the generic Hamiltonian can be written in this manner, and if you expand around the Weyl nodes, you see that that's the structure. So this is your Dirac structure. In addition, you could have a velocity which essentially tilts these Weyl nodes. And if this tilt angle is small, you have closed contours in momentum, closed constant energy contours in momentum space, and these are called type 1 Weyl semimetals. And if you have a really large V0, then these contours become open, and these are called type 2 semimetals. So for most of the talk today, I'm going to focus on type 1 semimetals. So there are several unconventional properties of these Weyl semimetals for which they are well known. So the first one is, of course, this Fermi arcs. I don't want to discuss this in details because this is so well known. Many people must have talked about this. There is also this chiral anomaly where by applying an electric and magnetic field in the same direction, you could have flow of electrons from one Weyl point to the other, and therefore a non-conservation of density. There is a quadratic dependence on magnetoconductivity and negative magnetoresistance, anomalous Hall effect, and axion electrodynamics. All of these are unconventional properties which are typical of Weyl semimetals and are not seen in standard materials. And there have been some recent experiment on tantalum arsenide where one has actually by RPS detected these Weyl nodes. And there are 2 groups, one in Princeton, another in China, and both of them have sort of looked at this material and have obtained similar results. So it seems at least that this particular material, which is a parity symmetry broken Weyl semimetal, not time reversal symmetry broken, seems to be a good candidate for this kind of metals. So having said that, let me just come to a brief introduction about this multi-Weyl semimetals, which is another type of material. Well, this hasn't been experimentally observed, but it has been theoretically proposed from Barnavik's group that Weyl nodes with same chirality make Weyls under certain circumstances. And apparently you need some special point group symmetries for this to be robust. So the way one understands this, at least in this compound, what happens is that the discrete rotation symmetry Cm, which is m-fold rotation about the z-axis, is the symmetry responsible for stability. So in the presence of such discrete symmetry, what you can see is that the Hamiltonian would satisfy something like this. That is, if you, and if there is a axis of this symmetry, which is here the rotation axis, you know that around that axis, this rotation matrix Rm acting on K would give you back K because it doesn't do anything around that axis. And therefore, from this relation, you see that Cm and H, they commute, and therefore one can sort of classify the, this Hamiltonian according to eigenvalues of, eigenstates can be leveled by eigenvalues of Cm as well. Now you take this and then you try to sort of stay on a momentum which is on this symmetry axis and expand for small momentum around any point on that symmetry axis and see what the effective Hamiltonian is. And what Barnavik's group through their analysis showed that the effective Hamiltonian would be linear in the symmetry direction, but perpendicular to the symmetry direction there may be different structures, and one of them, which is important for our purpose, is the one in which your bands perpendicular to that symmetry direction goes to zero around that touching point, not linearly, but either quadratically or cubically, where this j can take values 2 or 3 or something like that, some such integer. Okay. So 2 or 3 are the only known integers, and that is found in their work. So essentially, you can have a band which disperses linearly around along the symmetry direction, which would be z in this work. However, perpendicular to the symmetry direction, it's a quadratic or a cubic touching of bands. So the main point here is that, so there are several properties of this multi-Weyl semimetal which distinguishes them from Weyl semimetals. And one of them is that the topological charge or the topological winding number of this Weyl nodes is just this J, which is the index, which is the power at which the energy goes to zero from the transverse direction when you approach the crossing point. Okay. And this shows up in different quantities. For example, if you have optical conductivity or DC Hall conductivity, their behavior depends on this index, on this topological winding number J, and therefore they are different compared to their Weyl counterpart. And and the typical Hamiltonian for this kind of systems is something like this. You have a linear dispersion along Z, but a nonlinear dispersion along the transverse direction. Here the phi is the azimuthal angle in the transverse direction, and p parp is the absolute value of the, well, the magnitude of the transverse momentum. So junctions between Weyl semimetals, just like junctions between Dirac, so junctions between graphene has also been studied, and recently by this group. And it was found that if you induce superconductivity by proximity effect in one of these Weyl semimetals and put it up against another, which is normal, such in normal metal superconducting junctions, the NS junctions essentially shows these oscillations as a function of the intermediate barrier strength. And this is somewhat similar to what you see in graphene. Okay. What we are going to look at, and that's the main point of this talk, is that we are going to think of a junction which has a Weyl semimetal on one side and a multi-Weyl semimetal on the other. First, I'm going to talk about the situation where both the Weyl and the multi-Weyl semimetal is in normal state, and I have put a barrier in between. So this, as I showed, I mean this, this multi-Weyl semimetal. So let me just say that I have a multi-Weyl semimetal whose topological winding number is given by N1. Okay, and that multi-Weyl semimetal has a Hamiltonian which has a linear dispersion along the Z direction, which is my symmetry axis, and a nonlinear dispersion in the transverse direction. So I can just solve this Hamiltonian and get the wave function for a right or left moving electron, which obeys this Weyl Hamiltonian. And essentially, when I do that, the first thing, and this would be the key observation that I will make, is that the azimuthal angle dependence, the phi k dependence of the wave function, can be interpreted as a rotation by n1 phi k around the z axis. Okay, this tau z matrix appear here, and therefore this phi k dependence is just like a spin rotation around the z axis. Okay, and the rest part of the wave function, okay, if you take out this phase factor, is independent of the azimuthal angle. It just depends on the absolute value of the transverse momentum as well as the energy. Okay. So similarly, if you put in a potential barrier along with this Hamiltonian, you are going to get a similar structure. Okay. Now let me try to picturize an NBN junction for you, where I have a Weyl semimetal of topological winding number N1 in region 1 and 2, and that of N2 in region 3. And I would like to, yeah. I'm sorry? Yeah. Just one node. Yeah, so if you have multiple nodes which are not connected, then it will just be addition. You just multiply the whole result by the number of nodes. Okay, so that's all. Independent nodes, so to speak. So, and the Hamiltonian is given by H1 in this region, H1 plus U0 in this region 2, and H2 in region 3. Okay. And H2 corresponds to a topological winding number of N2, and H3 corresponds to a topological winding number of N2, and H1 and H2 corresponds to a topological winding number N1. So here in this kind of junctions, and this is one of the central points, is that the topological winding number changes across the junction. Okay? And these are, so we call them topological junctions in subsets. Okay? So as you move from region 1 to 3, there is a change in topological winding number. So this is a simple example of a standard calculation. So where you want to put in an electron in region 1 and then try to calculate the reflection and transmission coefficient. And this can be easily done. Okay. So okay. So before getting into the details of the calculation, here is the wave function in region 3. And what I would like to say is that here, the phi k dependence is rotation by n2 times phi k along the z-axis in spin space. Okay. And psi 3 alpha, just like psi 1 alpha, doesn't depend on the azimuthal angle. So what we do is we match the boundary conditions as x equal to 0 and x equal to d, and then obtain the transmission, calculate the conductance. Okay, that's a standard thing. Now, first, let me look into the thin barrier limit, where the barrier width is small and the barrier strength is large, so that their product is a constant. So what happens is that in the thin barrier limit, if I look at the boundary condition, it turns out that the boundary condition is that psi 1 just at z equal to 0 minus, that is just at z equal to 0, is some exponential factor which has the dimensionless barrier potential times psi 3. Okay. And you see that because I have put d to almost close to 0, there is just one boundary condition, and that comes as a discontinuity in the phase of the wave function across the boundary. Okay. That's a typical thing for most of this Dirac and Weyl semi-metals. Now the point is that because psi 1 and psi 3 has specific azimuthal angle dependence, I can use those. So for example, as I showed, that's for psi 3 I have I to the power minus I tau z n2 phi k by 2. So I can simply use that and write this in terms of psi 1 alpha and psi 3 alpha. And remember that the psi 3 alpha and psi 1 alpha is independent of phase. So whatever solution of R and T I find from this equation, the azimuthal angle dependence comes to this particular combination. Okay, because that's the only combination of phi k dependence that enters this equation. And indeed, if you do this calculation, which is reasonably simple, you see that it's this particular combination that comes out. Okay. So the point is then that chi, this dimensionless barrier potential, appears as a shift of phi k, okay, provided there is a change in topological winding number across the junction, provided n1 is not equal to n2. Okay. If that's the case, then when I sum over my azimuthal angle, phi k, since this chi appears as a constant shift, it doesn't really enter into any quantity which is obtained by summing over phi k. Okay. Because if you take an integral of this over phi k, it will be chi independent. Okay. That's relatively straightforward to see. And therefore, conductance, which is a quantity which you calculate by summing over all parallel modes, which includes an integral over phi, becomes independent of the barrier potential in this limit. Okay. And this only happens if the topological number across the junction changes. If n1 is equal to n2, that is, if you have two Weyl semi-metals with the same topological index, you see that you are left with a to the power I tau z 2 chi, which essentially, chi, which essentially means that you are going to have oscillatory dependence on chi when you calculate this. Okay. So just put N1 equal to N2 here, and you see that the transmission is an oscillatory function of chi. So this property, this independence, is a consequence of change of topological number across the junction. Okay, so it's essentially topology related. And so we look at this. You see, without getting into the details, it's really getting late. So let me just point out that this, the red and the green dots corresponds to cases where N1 is 1 and N2 is 2. That's for the red dots out here. And this is N1 is 2 and N2 is 3. So these are pretty much the same thing. But the point is that the dots and the lines just correspond to the same conductance, but for two different values of chi. One for chi equal to 0, the other for chi equal to pi by 4. Just two arbitrary numbers that we choose. And you see that they fall right on top of each other. And here is a better picture which shows the tunneling conductance as a function of chi. Whenever N1 is not equal to N2, it's just two numbers, which is absolutely constant. And if you have G over G naught for N1 equal to N2, the same conductance essentially is an oscillatory function. So you see that this property is completely different compared to the standard oscillatory behavior in topological junctions. So we shifted gear and looked at not so thin barriers. So we now do not put this V naught to be large and D to be small. We just keep independent values of U naught and D. And essentially we find that for different values of D, this oscillation starts developing. So there are extra oscillations if you are not in the thin barrier limit. But this amplitude of oscillation for a wide range of D and U is very, very small. That's much smaller compared to the oscillations you have for N1 or N2. So in a realistic junctions, provided you can make one of these, it should be robust against, having slightly thick barriers. So now what I want to do is I want to put a superconductivity in region 3, that is make the multi-Weyl semi-metal in region 3 to be a superconductor by putting in approximate induced SOA pairing. And this has already been looked into by other groups. The point is I'll just take their model for this proximity induced SOA pairing. So, and the pairing would be between electrons and Weyl node with same chirality. And it's a SOA pairing, and that's the one preferred in low energy sector in this kind of materials. So essentially all you do is to do the same thing, but solve for now the electron-like and hole-like quasi-particle wave functions, which is standard. But the point is that even for this Hamiltonian, what we find is that the superconducting wave function again has this property that the phi k dependence can be understood as a rotation around the z-axis by n2 times phi k. Okay, so that's the property that we need. And okay, let me just skip those details. I mean, so after some calculations, we again find that this is the boundary conditions that we find. Again, everything appears as a function of cos N1 cosine and sines of this particular combination, and therefore the transmission becomes barrier independent. In particular, if we look at subgap tunneling conductance as a as a function of voltage, these again are data for chi equal to 0 and chi equal to pi by 4, and you see that they fall on top of each other, which essentially tells you that the barrier potential doesn't change the subgap tunneling conductance out here. And there is some reason why. So let me just point out why you have subgap. So we find that there is a finite subgap tunneling conductance only if N1 is greater than N2, and let me point out why the reason is. So so we have in this case taken large chemical potential both in the superconductor and the normal region. And it turns out that the angle of these quasi-particles in which the quasi-particles move in region 3 is related to the angle in which they move in region 1 with this relation in this limit where mu n and mu s are large and equal to one another. And there is a factor of mu n times n2 by n1 minus 1. Now, the point is if n2 is greater than n1, this means that this sine 2 theta 3 now becomes sinh of 2 theta 3. And if this quantity is large, what happens is that it's roughly exponential. So this kind of sign factors get into this tunneling conductance, both in the numerator and the denominator. But the upshot of this being exponential turns out is that the final undrift tunneling conductance, which is responsible for conduction within the gap, essentially decays exponentially with this mu n. Okay, and if mu n is large, this is almost close to 0. So we have checked by varying mu n that this exponential variation is can be seen. The point is that the voltage dependence of the subgap tunneling conductance is therefore controlled by this ratio of N2 by N1. So whether you have a finite subgap tunneling conductance or a zero subgap tunneling conductance, that depends on the ratio between this topological winding numbers. So finally, this is the zero bias tunneling conductance as a function of chi when N1 is not equal to N2 and when N1 is equal to N2, and you clearly see the difference. So just to point out that the change in topological winding number across the junction nullifies the effect of junction barrier potential in the thin barrier limit, and therefore gives you a barrier independent zero bias tunneling conductance. Since this requires at least 2 transverse dimensions, you don't see this in graphene or surface of topological insulators, because you need to have an azimuthal angle for this kind of physics to come up. And you also need the topological winding number to change across the junction, which is also not seen in graphene or topological insulator junctions. So this is a property which is going to show up only in 3D, and the junction of Weyl and Multi-Weyl semi-metal is an example out here. Now the question is, how do you get these junctions? It's not so easy. I mean, these two are different junctions, and it's not, different materials, and it's not easy to form junctions. But the point is, what one can do is to take 2 pieces of same multi-Weyl semi-metals and apply local strain on one of them. Now, what strain does is to change, sort of spoil the CM rotational symmetry of this multi-Weyl semi-metals, in which case they can be converted into a Weyl semi-metal. So the different Weyl nodes which coalesce to form a multi-Weyl node, they get separated, which was first pointed out by Barnavik and later calculated by others. So a sufficient amount of strain can convert a multi-Weyl semi-metal to a Weyl. And so the prediction is that as a function of strain, your amplitude of oscillation of this tunneling conductance is going to reduce and ultimately come to 0 if you can provide a sufficiently large strain on one side of your junction between 2 multi-Weyl semi-metals. And that, I think, is the easiest way of looking into this experimental way. So to conclude, what we have seen is that this topological materials provides really interesting tunneling conductance and their barrier dependence. And here is one where the barrier becomes, the tunneling conductance become completely independent of the barrier strength. And this is a consequence of the change in topological winding number across the junction, across which you are calculating the tunneling conductance. So I think I'm going to stop here, and thank you for your attention.
Chen's comments. Suppose you don't have S-wave like superconducting order in one of the Weyl junctions, one of the Weyl leads. What happens if there are other kinds of superconductivity?
Not sure how it is going to turn up, but this particular property, I think, is going to stay. But the details of the tunneling conductance will change for sure. But this barrier independence, I think, is going to stay, because it's really a property of the fact that so in the thin barrier limit, when you are matching boundary conditions, the entire thing appears as a phase factor. So that's what, and that, I think, would be there, because it separately holds for electrons and holes. It also holds for any kind of quasi-particles, superconducting quasi-particles that you will have. And therefore, I would expect that property to hold for other superconductors. But other details are surely going to change. I haven't calculated those, so don't really know how it's going to.
Often it's very likely that if you have such low energy excitations, which are Weyl-like, you can have
other ways.
Conventional superconductor.
Yeah, sure. Yeah. I just took one model, where it was SOF, but you could have other models where it won't be SOF. Sure. Yeah, Ying-Jer.
I wonder what if I turn on AC, what kind of AC response would you expect from?
Well, okay, so you mean for this kind of this thing? No, I haven't really looked at the AC context in this AC thing in this context. But I can tell you that if you make a Josephson junction out of this, again, two superconductors and you put this, then yeah, sure. Then you are going to find that this Josephson current again is going to be independent of the critical current is going to be independent of chi. And also there is another very interesting feature is that as you know, I mean Josephson junctions are characterized by the product of their critical current times their normal state resistance, right? This IC times Rn, that value. Now, if a barrier essentially is almost transparent, this value in some units of pi delta naught over 2iz, pi b, I mean delta naught being the barrier amplitude and E being the electron charge, is essentially 2, and that's your Kulikov-Mellowentschuk limit. And if it's a really strong barrier, then it is 1, which is your Ambegaukar-Baratov limit. These are the two limits between which these materials, and this is something that we have calculated, has a fixed value between 1 and 2, and they just sit there. Because if you change the barrier, your IC doesn't change, and you cannot really tune it from one limit to another. It's a truly universal number for this kind of superconducting junctions. And AC response for this is also going to show up in the sense that one thing that is going to happen is that if you put a AC microwave radiation, you are going to see Shapiro steps. The width of these steps is going to be independent of whatever barrier you put. That's not the usual thing in superconducting junctions. So that's another way of looking at this. So, yeah.
So there are no more questions. Let's thank the speaker. This session is over.